Welcome back again. I'm here now to substitute our colleague Ana Carreira because she's not possible to be here. And I ask the participants, if you want to make questions for the speakers, to send directly to the Congress email or to use my email that is now on the comment section on the screen. So you can use both the Congress or my personal email. I will start the presentations in sequence, and the speakers first will speak Francisca Silva, which she is a student in biomedical science at the University of Vera Interior. The following will be Álvaro Vaz, who is a researcher at the FibEnTech at UBI, following Flávia Moraes, a researcher also in the FibEnTech in UBI. And the last presentations will be done by Mohit Sharma, a researcher in Chemical Processing Engineering and Forest Products Research Center at the University of Coimbra, following Manorma Sharma, also a researcher in the Chemical Process Engineering and Forest Products Research Center.
My name is Francisca Silva, and today I'm presenting the assessment of autofocus techniques for isolated cellulose microfiber 3D imaging by digital holography. So, digital holography is a powerful 3D imaging methodology that is particularly suited to microscopy applications. This is achieved by encoding the wave field transmitted or scattered by an object in the form of an interference pattern with a reference beam. While in conventional imaging systems, it is almost impossible to retrieve the correct focus image from a blur, with digital holography, the image can be retrieved numerically at any distance from the hologram. One of the advantages of this high-resolution method is the ability to perform numerical refocusing at several depths from a single-shot acquisition. Inline digital holography is characterized by its ability to image intensity and amplitude of objects with sub-micrometer resolution. Hologram reconstructions transforms also provide access to phase information and images of the spatial variations of phase changes of wavefronts in the optical field are easily created. Quantitative determination of phase changes is an integral part of inline digital holographic microscopy, so that unlike the situation in conventional optical phase microscopy, a quantitative determination of the optical path through an object is easily performed. Classic interferometric phase shift measurements are capable of very high sensitive, but are often difficult to employ. The simplicity of this technique makes it of great interest to determine the extent to which accurate optical path measurements on micrometer-sized objects are possible. Furthermore, the inline configuration of digital holography enables highly compact setups with digital autofocus capabilities. These features allow to overcome typical runout and jitter constraints inherent to conventional optical tomography. This phenomenon results from misalignments and vibrations in the signal acquisition phase due to sample rotation. The multi-view or phase reconstruction capability has the potential to allow the reduction of the number of acquisitions, making the recording process faster. In this work, the suitability of 22 focusing functions to accurately identify the positions of cellulose microfibers using digital holography is inspected. The best performing metrics were identified, and the trade-off between metrics accuracy and robustness to variable conditions and their computational complexity was discussed. So, to test the selected focusing criteria, digital holograms of a set of objects, including a USAF 1951 standard resolution target and two types of plant microfibers, eucalyptus and pine tree, were selected. An inline Geber digital holography setup using an Ilion neon laser with 5 milliwatts and 632.8 nanometers of wavelength for sample illumination, as shown in this figure. The interference patterns were digitalized by Guppy Pro F 503 camera, having a CMOS sensor with 2.2 micrometers square pixel size, using an acquisition mode with 2,588 per 1,940 pixels of resolution and 8-bit depth. So each hologram results from a pair of interference patterns, where the first is the test hologram recorded with the sample in place, and the second is a reference hologram recorded without sample to remove a background noise. To obtain the reconstructed complex object field, we applied an algorithm consisting of a Fourier transform of the digital hologram. This is further multiplied by a transfer function, followed by an inverse Fourier transform. The procedure is called the angular spectrum method, ASM, and has the advantage of keeping the pixel size independent of the reconstruction distance. Here we have the cropped areas from reconstructed holograms at best focus distance obtained from the average results of the set of focus metrics. So this one is from the target USAF 1951. This one is from the eucalyptus microfibers, and this one for the pine tree microfibers. To perform an automatic focus on a sequence of reconstructed holograms, 100 numerical reconstructions were computed in intervals ranging from 1 to 2 millimeters, depending on the sample. Then, for each reconstructed amplitude, the focusing metrics, which are basically contrast-sensitive imaging processing algorithms, were applied. 22 metrics were selected from a preliminary set of focusing metrics that performed well in phase-shifting digital holograms and the study concerning sparsity metrics. Furthermore, these metrics were grouped in 4 categories according to their mathematical similarities. Group A, with image statistical or spatial properties-based metrics. Group B, with wavelet or spectral-based metrics. Group C, sparsity metrics. And Group D, LP norm-based sparsity metrics. To compare the results of different focus measures, a set of performance criteria related to unimodality, accuracy, AM, resolution, RM, and range was used. Since only amplitude or mixed amplitude holograms were tested in this study, the above-mentioned metrics all should yield a maximum at the in-focus position ZF after proper normalization of the focus curves. The trade-off between performance metrics and computational burden is also inspected using the mean computation time at a given step of the search interval for each of the 22 focus algorithms. So, 22 focusing metrics were tested on a calibration object, and several types of plant fibers, from which 2 were selected: a sample of eucalyptus microfibers and a sample of pine tree microfibers. Since the distances from the camera to the sample holder were small, the amplitude spectrum method was used for numerical reconstruction of the acquired holograms. Small distances are recommended for best spatial resolution. The results were compared for each sample, and the amplitude input proved itself a more reliable option with less cases of failure to identify a peak value. The 2 sets of data were further divided in 2 cases regarding reconstruction resolution. One set comprised full-sized reconstructions with square resolutions of 1940 per 1940 pixels, and a set of interactively selected cropped reconstructions with lower resolutions, about surrounding the region of interest in each case. In the later case, the idea was to promote a much faster focusing procedure without sacrificing the focusing performance. The second approach not only revealed to be faster, but also more effective in most cases. Thus, the following presented results relate mainly to the case of cropped region of interest of amplitude inputs to the tested focus functions. This table was selected from a set of results to illustrate the behavior of the tested metrics when using an object with different scales of resolution, such as the USAF 1951. Using this target also allowed an appraisal of the resolution capability of the setup used in this work. The values highlighted are the 3 most performing metrics values in terms of accuracy, fidelity, and resolution. The focusing curves obtained from microfiber samples show the smoother behavior except for the Gini index and the norm. This is likely due to less abrupt refractive index changes and consequent absence of speckle noise. The LAP and the FSL metrics yield the best accuracy value for all the tested samples. However, they fail to fulfill the unimodality criteria over most of the samples. Wider metrics such as the VAR or sparsity-based LP and L1 norms tend to be more reliable, although they may not be so useful when the separation of different layers with individual particles of features is intended, such as in particle tracking applications. Here we can see the eucalyptus microfibers. We have a much smoother graphic. Another important aspect of a focus metrics performance it is computational complexity. Thus, to access the efficiency of each algorithm, the mean and standard deviation of the computation time for the calculation each focus measured for a given step of the search interval was computed. The tests were performed on the USAF 1951 reconstructions. It can be observed that among the most performing metrics in terms of correct identification of the focus distance, the sparsity-based metrics, LP, L1, and L2 over L1 norms have the additional advantage of being very fast. Furthermore, as pointed out earlier, these metrics are widely employed in compressive sensing methods, thus showing a promising value in the development of a new simultaneous reconstruction method for improved resolution and noise reduction. So, in conclusion, the present results illustrate the importance of choosing a highly performing autofocus method for inline digital holography of plant microfibers. The nature of each tested sample has an impact in this choice, with the diversity of feature size and axial location of different objects within the sample, leading to stronger differences between focus criteria. For a coarse initial location of a given microstructure, faster and more robust, but less precise metrics such as the VAR or sparsity-based LP and L1 norms tend to be more reliable and can be embedded in comprehensive sensing algorithms. The LAP and the FSL metrics yield to best accuracy value, but can only be applied to narrow range intervals due to lack of unimodality. More elaborated metrics, such as the Ward fields, help distinguishing structures buried at distinct depths, at the cost of a high computation complexity. Preliminary results show that magnified holograms are more demanding in terms of autofocus robustness to misalignment and noise issues. In this case, the statistically based metrics such as VAR and Wolf5 and the sparsity-based metrics such as the Gini index have shown better performance so far. Finally, I would like to thank to the Fiber Materials and Environment Technologies for having me today. I hope you liked it. Thank you very much and goodbye.
Hello, my name is Álvaro and I belong to FibEnTech Research Unit and the Chemistry Department of University of Vera Interior. I'm going to present the work A Globulus Vessel and Fiber Chemical Analysis, which was done with the collaboration of Instituto Superior Técnico, Alto University and Reis. This work was carried out under the project Impactus. The presentation plan is the following. Point 1, problematics. Point 2, vessel quantification and morphological characterization. Point 3, vessel separation methods, selection and optimization. And point 4, vessel and fiber chemical characterization. Point 5, and the final point, is main conclusions. This is the scheme of the problematics of our work. It's relating with printing problems, resulting from two problems: vessel peaking due to vessel lack of adhesion and ink refusal due to vessel hydrophobicity. Our general plan and strategy was first to measure vessel biometric characterization, then study the vessel surface chemistry. We also studied methodologies for vessel separation and devised strategies for vessel passivation, conjugated with mechanical treatment called refining, and also surface treatment, chemical and enzymatic. And those strategies must improve printing properties in terms of vessel peaking and ink refusal. The point vessel quantification and morphological characterization includes the parameters of dimensional morphology of each kraft pulp E globulus vessel by light microscopy and also of fiber. Vessel quantification methodology by optical microscopic methods, vessel characterization and quantification with microfiber analyzer module, and primary morphological quantification of a globulus vessel with microfiber analyzer. In terms of optical microscopy, we have two pictures showing vessel and fibers with 100 times amplification and 400 times amplification, focusing on one specific globulus vessel. And on the left we have the equipment that was used. The general vessel properties, the width was between 70 micrometers and 150 micrometers, and the length was between 200 micrometers and 500 micrometers. In terms of microfiber analyzer, it uses a methodology of taking images and doing image analysis on pulp suspension. There is a model which studies also the number and characteristics of vessels, which we show here. The main results in terms of globulus bleached kraft pulp in Morphy analyzer, the fiber number was around 30 million fibers per gram, and the vessel numbers was around 0.14 or 15 million vessels per gram, which gave a ratio of fibers and vessel of 266. In terms of area, the surface area on the pictures, the vessels, it was around 3.8%, and fines around close to 12%. In terms of the results of fiber elements basic morphology for eucalyptus, the length of fibers was around 1072, its diameter 15.9, and shape factor of 67.4. For the vessels, the length was around 300 and diameter around 154, which gave a shape factor L over D of 1.95. The Morphy analyzer also gives other general factors such as coarseness, the ratio of mass over length in terms of milligrams per 100 meters of fibers, which is 6.1 for eucalyptus globulus, and other parameters such as curl, kink angle, kink percentage, microfibrils, and broken fibers. The next point is vessel separation methods, selection, and optimization, where we devised several methodologies for vessel separation in order to make chemical analysis and physicals also. The first point was to separate using Bauer magnet. It's an equipment with a series of screens, and we also made essays with the so-called Jacqueline method, and also we used Bridge-Jar separation. The results for eucalyptus globulus showed that the highest ratio was obtained of the highest ratio of vessels comparatively to fibers, also obtained on screen mesh 15. We also used mesh 30 and mesh 200. One method to separate this previous method was able to clean the fibers, the pulp from fines, and also to separate the long fibers, very long fibers. The Jacqueline method was devised by Jacqueline in 1972 and was theoretically expanded by Sozinski in 1987. And the principle is the rotation that causes flocculation, and the fibers and vessels are kept out of the flocks and concentrate out of the flocks. The ideal peripheral speed for eucalyptus globulus, according to Sozinski and Jacqueline, is 30 meters per minute at a consistency of 1.5 with a method using roto-evaporator and agitation rotor. Those were the two strategies. The rotor evaporator was closest to ideal method, but only produced in terms of the hydrodynamic, but just produced a rotation speed of 3 meters per minute. The agitation impeller was closer to ideal peripheral speed, but the hydrodynamic was further from the ideal. Here we have two pictures showing the result of Jacqueline method. On the left, we see the flocculation, and on the right we see optical microscopic image 40 times, where we see the flocks and the vessels. We also devised a system of separating the parenchyma in order to clean the pulp suspension, the mixture of fibers and vessels. We also used a breath dynamic drainage jar in an original trial, which was done with a single screen and a continuous flow of water. Then we obtained the following results shown in the images. What was the problem with this system? Besides the high consumption of water and long time also, there was a residual high quantity of long fibers that must be separated. So we devised a second method inspired by Orber, Lindström and Fartin paper of 2012, where the conical nets were used with opening 157 micrometer, a consistency of 1%, with previous air drying for 3 days. We devised a 2 steps closed system with recirculation. First, we concentrated the vessels within the recipient, within the breath jar, as we can see here, with a screen of 177 micrometers to retain the vessels. the recirculation retained the fibers that passed through the screen in a screen of mesh 400. In a second step, we opened up the conical holes in the screen and to retain the fibers and let the vessels pass. And also the vessels in the recirculation are kept in mesh 400 screen. The results are quite good, as we can see here in these images. A problem that we faced due to the need of higher quantities of vessel is the level of production. So we tried to make a scale-up prototype that in terms of the breech jar, which we have used, and then we devised other scale-up which are not explained here, which is not explained here. Now I pass on to the vessel and fiber chemical characterization. We did some optical analysis. We have here a picture. The EDX elemental composition was also done, and we obtained different OC ratios for fibers and vessels, being the OC ratio on fibers higher, 0.9 against 0.7 in vessels. We also did, with collaboration of Instituto Superior Técnico, with Professor Bordado, Professor Ana Marques, and Dr. Rui Galhano, using a Perkin-Elmer microfiber that was used. The main results, which was done and compiled by Professor Ana Marques, is that the spectra obtained from vessels and fibers are very similar, but there is mainly a difference in the peaks relative to CH bonds and to COC ether group. The vessel spectra typically have a slightly higher peak at circa at around 900 per centimeters, CH stretch and COC stretch 1105 per centimeter, COC strain, and 1160 per centimeter aromatic CH strain in plane asymmetric CC stretch. The presence of higher hydrocarbon concentration may be related to the higher hydrophobicity presented by the vessels. As a conclusion to these results and analysis. Here we have the image of the different microfibers of some of the microfibers that were done. Here we have the microfiber for an eucalyptus fiber, and here for 2 points in a vessel of a globulus. And here we have the general diagrams and analysis. And the general conclusion, we have the different points which are marked and can be seen in detail in our paper. And what you can see that probably vessel in globulus are more hydrophobic due to more CH, CH2, and more COC. We also did chemical analysis. We analyzed what we call XMG, which is cellulose, mannose, and galactose, which is related to hemicellulose content, hyaluronic acid, total acids, and zeta potential. What you can see is that vessels hemicellulose content is higher, and the vessels are also more acidic in terms of total acids and hyaluronic acid content. And also that fibers are more anionic. Here we have compilation of the global results. XMG content in vessel is 35% higher than in fiber, thus having a higher hemicellulose percentage. Concerning acidity, the total acids content is also higher in vessels, 12%, while the hyaluronic content is even relatively higher. Zeta potential values indicate that fibers are more anionic than vessels. Main conclusions. I pass on to main conclusions. In terms of separation methods, it was devised the size exclusion methodology into steps preceded by fine removal with Bauer magnet. ADX revealed to us lower OC ratio observed in vessels, possibly explained by higher lignin and extractives content. Microfiber, the spectra obtained from vessels and fibers are very similar, but there is mainly a difference in the peaks relative to CH bonds and to COC ether groups. The possible presence of higher hydrocarbons concentration may be related to the higher hydrophobicity shown by vessels. Chemical analysis. Vessels have a higher hemicellulose content, higher acidity, and higher hyaluronic acids content, nevertheless being less anionic than fibers. I thank you for your attention, and I finish here my presentation, and we are open for questions. Thank you.
Good afternoon, everyone. My name is Flavia Moraes. I'm currently finished my PhD in Fibrous Material Science and Engineering, and today I'm going to present one of the works that I've been doing. My presentation is entitled Development of Sustainable Cellulose-based Tissue Materials using an Innovative Experimental and Computational Methodology. Tissue paper materials such as toilet papers, towel papers, napkins, and facial tissue papers are known for their creping and embossing operations, low basis weight, high porosity, bulk, softness, strength, and absorption properties. Therefore, the production of tissue paper materials requires the furnish optimization. These tissue furnish include hardwood pulp, softwood pulps, and additives. In an overview, the strategy used in this work can be separated in three fundamental sections. The first, the 3D fiber characterization and modeling, in which fibers and 3D structures are characterized and modeled according to their dimensions and properties. The second, the fiber and structure modification process, using experimental and computational approaches to evaluate the enzymatic and mechanical treatments and additives incorporation. And finally, the optimization using advanced computational tools to develop from scratch and validate a simulator for furnish optimization and management of an industrial process, the seam tissue. Tissue papers are produced using sustainable cellulose-based materials like hardwood pulps and softwood pulps. Hardwood pulps are used to improve formation and softness, while softwood pulps are used to ensure strength and paper machine runnability. Therefore, hardwood pulps present the potential to be optimized to improve their mechanical properties while maintaining existing benefits. This is important to maximize the tissue functional properties such as softness, strength, and absorption. This is achieved using the fiber and structure modification process. Sustainability is a major focus of the tissue paper industry. So, one strategy is the development of environmentally friendly enzyme technologies to improve the efficiency of energy management in the tissue process. Celluloses are the most used enzymes because they improve the fibrillation and cellulose fibers and prepare them for the mechanical process. This includes less mechanical stress to the fibers and has a positive impact on tissue properties. Another strategy is the incorporation of additives to improve tissue properties and the production process. Examples are micro-nanofibrillated cellulose and biopolymers. So, the tissue furnace optimization process requires extensive research and methodologies to overcome the issues, which involves the design and analysis of laboratory and computational experiences. The development of advanced computational tools with predictive capability for furnish allows to estimate which raw materials are most promising for a particular tissue product and estimate which process operation allowed to obtain tissue with desired and optimized properties. So the experimental planning consisted of the selection of different cellulose pulps obtained from species and process of industrial interest. The fibers were modified and optimized for softness, strength, and absorption properties using enzymes and mechanical treatment. The incorporation of different additives was also investigated, namely the incorporation of micro-nanofibrillated cellulose and biopolymers. The relationships between these properties were established using different innovative computational tools and simulation and experimental data to obtain predictive capability. Then the structures were simulated in 3D to validate this model, and this entire process allowed the computational implementation of the seam tissue to be used in specific cases to support furnace industrial management and optimization, and to design innovative premium tissue materials. So, the seam tissue establishes relationships between input variables of fiber properties and output variables of tissue functional properties, quantifies the change that occur due to the use of different pulps and process operations of tissue paper production, investigates the different furnish scenarios with industrial interest, including different pulp combinations, and the design and optimization of each tissue product. Finally, the seam tissue supports industrial furnish management, considering also structures with scraping and converting operations. This table outlines examples of scenarios that can be selected in the seam tissue. So, for example, the simulations can be performed by selecting a percentage of hardwood pulps of industrial interest, another percentage of softwood pulps or other hardwood pulps. Select if any pulp can or cannot have enzymatic and mechanical treatment, identifying the respective conditions, and also if in furnished formulation there is the possibility of incorporating additives. Therefore, the seam tissue predicts the influence of various types of raw materials, process operations, and additives at micro and nano scale. An important achievement is the comparison of structures produced with different formulations. In this work, we present different comparative scenarios of case studies predicted by seam tissue compared to typical industrial formulations, namely 75% of hardwood pulps and 25% of softwood pulps. The properties of these formulations are presented here, as you can see. Regarding the fiber mixtures, this figure presents the percentage of variation in the final end-use tissue properties for formulations with different fibrous composition. The results indicated that the reduction of softwoods improved softness and absorption and decreased the strength properties. It was found that the softwood fibers remain an important element to confer strength and absorption properties, especially in products such as wet-strength papers. Additionally, the formulation with 10% of softwood fibers presented a balance between the tissue properties and present the highest potential to replace the industrial reference. Regarding the incorporation of additives, these figures present the percentage of variation in the final end-use tissue properties for formulations with micro-nanofibrillated cellulose incorporation. So the results indicated that the replacement of softwood fibers by micro-nanofibrillated cellulose improved softness and decreased the strength and absorption properties. It was found that micro-nanofibrillated cellulose presents a good potential to be used in tissue products such as toilet and facial papers. Additionally, the formulation with 5% of micro-nanofibrillated cellulose presents a balance between the softness and tensile index properties with the highest potential to replace the industrial reference. Also, the formulation with hardwood pulps, softwood pulps, and micro-nanofibrillated cellulose also present a good combination between softness, strength, and absorption properties essential to produce premium materials. So, still in the incorporation of additives, these figures present the percentage of variation in the final end-use tissue properties for formulations with commercial biopolymer incorporation. Overall, the incorporation of these additives increase the softness and absorption properties at the expense of decreasing strength up to 3% of incorporation. On the other hand, after the 4% incorporation, the softness and strength increased at the expense of absorption. Note also that the 4% of incorporation has practically the same tensile index values as the industrial reference. This means that this incorporation can allow the replacement of softwood fibers in terms of strength properties. Sim tissue also allows incorporating two additives in the formulations at the same time. The simulations were carried out to study the effect of combining two additives on tissue properties and to study their implication in softwood pulp reduction. These figures present the percentage of variation in the final end-use tissue properties for formulations with biopolymer and micro-nanofibrillated cellulose. The conditions of simulation 1 are presented here on the left, and the conditions of the simulations 2 are presented here on the right. The difference between them is the incorporation of hardwood and softwood pulps. The result indicated that with the softwood pulp reduction here in simulation 2, the additives incorporation promotes an increase in softness and absorption with good strength properties similar to commercial tissue papers like toilet papers. So, regarding the enzymatic treatments, this table presents the scenarios of the enzymatic treatments of different pulps, to kraft and sulfite pulps. Sim tissue predicts the formulation properties with variation in reaction time and enzyme dosage. In simulation studies for a kraft pulp, simulation 1 and simulation 2, similar properties are obtained with an enzyme reaction time of 30 minutes and with a dosage of 50 grams per ton, and also with twice of the enzyme reaction time and with a dose 60% lower. In simulation studies for a sulfite pulp, simulation 3 and simulation 4, similar properties are obtained with the enzyme reaction time of 30 minutes with a dosage of 100 grams per ton, or also with twice of enzyme reaction time and with a dosage 70% lower. Therefore, this suggests that tissue properties can be optimized by increasing the enzyme's reaction time, decreasing its dosage. Additionally, a design was proposed that combines 80% of the enzymatically treated kraft pulp and 20% of the sulfite pulp with and without enzymatic treatment. The conditions of these combinations are present here in this slide, as you can see, on both sides. And the results indicated that this combination increased softness with good tensile and absorption, ensuring the necessary strength to obtain premium tissue papers. The tensile index values of these combinations were higher than the values for commercial tissue papers like toilet papers. So, in this slide, we can see an example that hardwood pulps can be modified by a sustainable process to be used to produce tissue properties, allowing the reduction of softwood pulps in formulations. So, in conclusion, with this work was possible to develop and validate the sim tissue to optimize innovative furnish formulations, saving laboratory and industrial resources, identify the more suitable hardwood and softwood pulp from a collection of raw materials, and optimize different furnish formulations, including additives incorporation, enzyme dosage reduction, extending its reaction time, and energy gains. So, sim tissue is a computational tool with predictive capacity useful for furnish management and sustainable process optimization. This slide lists the publication in which you can find more detail about the experimental design and the computational tools. I would like to thank the project Impactus, Innovative Products and Technologies from Eucalyptus, and my research unit, FibEnTech, Fiber Materials and Environmental Technologies, and of course to my supervisors, Professor Joana Curta and Professor Maria Emília Amaral. So I finished my presentation. If you have any questions, don't hesitate to ask. And thank you all for your attention.
Hello, my name is Mohit Sharma. I am here to present a part of my PhD work, which is dynamic penetration profile of starch betainate, Pluronic and PCC coated papers. In this presentation, I start with the introduction cum motivation for this work, following with the different coating components which I use to prepare coating formulations. Further, I will talk about the dynamic contact angle and the penetration dynamic profile of those coated papers. At the end, I will sum up my presentation with concluding remarks. Paper requires surface treatment for improving their properties, such as sizing, barrier, and printing properties. In our project, we are focused to improve printing properties. Here, the paper surface are compared. It can be noticed that the presence of cationic polymer on the paper surface holds the ink pigments more on the paper surface, whereas those pigments pass the paper surface and go deeper in the paper matrix for paper without any surface treatment. To this motivation, we used a novel method to synthesize cationic starch. The reaction proceeds in two steps where betaine hydrochloride in the presence of thionyl chloride and methanol first converts in its ester form. This ester form of betaine hydrochloride then reacts with the starch to give starch betainate, which is a cationic starch ester. In this work, we used 0.3 of degree of substituted starch betainate. Going further, for another coating components, we use Pluronic, which is an amphiphilic polymer, and PCC. Here in the table, for each component, we use 8%, 16% and 24% of concentration for preparing coating formulations. And here in the table, their combination were used to coat the paper surface. We observed that the printing quality improves substantially with the synergetic effect of starch betainate and Pluronic. Printing quality of these coated papers are reported in our recent publication. Further, I will show one of the reasons behind the improving those properties. Apart from the positive charge on the paper surface, a quick absorption of the ink carrier solvent enhances the printing quality. Here we can see that when we apply only starch on the paper surface, which increases the hydrophobicity of the paper surface, whereas replacing some amount of the starch with the Pluronic, it shows a quick absorption of the water. In opposite trend, starch betainate shows similar hydrophobicity as native starch. However, the combination of starch betainate and Pluronic showed a higher hydrophilic surface properties. We also evaluate the water penetration profile using penetration dynamic analyzer. Blue line represents the starting of water absorption. In the case of starch betainate and PCC, it takes some initial time to start the penetration, whereas with the Pluronic it was very quick of absorption of water. The following trend shows the sizing of coated papers. Here it can be seen that the sizing was increased with increasing starch betainate and PCC concentration. Starting of water absorption was still the same as Pluronic coated paper for the combination thereof. A quick penetration of water and sufficient sizing degree can be seen in starch betainate, Pluronic and PCC coated papers, which are in good relationship with the higher printing qualities. I would like to conclude my presentation here with these remarks that the paper coated with starch betainate and Pluronic showed a high printing qualities, which was due to the presence of cationic charges on the paper surface and a quick absorption of water in their presence, which gives a higher absorption of ink carrier solvents and leave the ink pigments more on the paper surface, thus improve the printing quality of the paper. I would like to thank Project Impetus and my supervisor Professor Paulo Ferreira and Professor Arthur Valente, and also thank to FibEnTech organization committee to give me this opportunity to present my work here in this conference. Thank you for listening me.
Hello, my name is Manorma Sharma. I will talk about the recovery of biomaterials like lignin and hemicellulose from kraft black liquor. So the black liquor is generated as a side stream of the pulping process, and the most dominating pulping process is kraft pulping. In this process, wood is cooked with highly alkaline pulping liquor to remove the lignin. After pulping process, approximately 50% of biomass is converted to pulp, and rest 50%, which is mainly lignin and some amount of hemicellulose, get dissolved in the spent pulping liquor, which is generally referred as black liquor because of its dark color. This liquor is burned in the recovery system to recover the pulping chemicals, and lignin and hemicellulose, because of their heating value, generate steam and power for the paper industries. But this lignin and hemicellulose, because of their good potential, can be used for the production of high value products like absorbents, nanoparticles, biofuels, hydrogels, etc. But as recovery of pulping chemical is important for paper industry sustainability, so it is important to recover these biopolymers with minimum disturbance to the chemical recovery process. In that case, membrane filtration can be a best solution, as membrane can separate different components of a solution based on the difference in their charge density, solubility or molecular size, etc. We have the advantage of difference in molecular size for the various components present in black liquor. So, in our project, we filtered the black liquor by ultrafiltration membranes of 10 kilodalton molecular weight cutoff, and the inorganic content which was smaller in molecular size and the severely degraded organic content passed through these membranes with the permeate, and the big molecular size component, which were mainly lignin and hemicellulose, were retained by these membranes in the retentate stream. This retentate stream was used for the separation of these biopolymers, which were lignin and hemicellulose, for their separation. The lignin and hemicellulose separation was performed sequentially in two steps. In first step, lignin was precipitated by reducing the pH of black liquor, and pH was reduced in the range of 3.5 to 4.5. For black liquor acidification, different organic acids were analyzed as a greener alternative to sulfuric acid and phosphoric acid. In the second step, the supernatant of first step was used for hemicellulose recovery, and hemicellulose was precipitated by adding the acetone as antisolvent, and the effect of residual lignin in supernatant and the supernatant to antisolvent ratio was analyzed on the composition and yield of extracted hemicellulose. In this table, we can see that filtration of black liquor resulted into increased concentration of organics, and then in this figure we can see the performance of different organic and inorganic acid for separation of lignin from black liquor. We can observe that inorganic acids resulted into higher separation yield compared to organic acids. In case of organic acid, lactic acid gave similar yield like sulfuric acid and phosphoric acid, but the extract obtained from lactic acid contained higher inorganic content, while the extract obtained by acetic acid and citric acid has higher organic content, but citric acid resulted into the lowest yield of lignin. So due to high organic content and acceptable yield, the supernatant from acetic acid recovery was used for the separation of hemicellulose. Now for here we can see that yield of hemicellulose varied with the residual lignin concentration present in supernatant and with antisolvent to the supernatant ratio, and we obtained highest yield of approximately 54% at a condition where residual lignin concentration was low and the high antisolvent to the supernatant ratio was used for the precipitation. As the black liquor came from eucalyptus based kraft pulping process, so the main monosaccharides present in extract were xylose, arabinose and acetyl group, which was detected as acetic acid. And the extract was analyzed also for the composition of organic and inorganic part, and we can see that inorganic and organic content also varied with the residual lignin present in supernatant and the antisolvent to the supernatant ratio, and the inorganic content varied between 15 to 34% in different extracts. Finally, I can conclude that membrane filtration can not only control the molecular size distribution of the biopolymers in retentate, but also it can increase the purity of organic content compared to the inorganic content present in black liquor. The organic acids can be used as a greener alternative for the separation of lignin from black liquor. By using organic acid, which was acetic acid, we obtained 35% yield for the lignin, and from the supernatant of this process, we obtained 54% yield of hemicellulose from the concentrated black liquor. Finally, I would like to thank my project for funding my work, and thank you all for listening.
Hello. To start, I would like to thank the FibEnTech organization for the chance to participate in this event. My name is André Cunha from Universidade Vera Interior, and this work was guidance of Professor Rogério Simões. I will give a brief presentation of my last work, the effect of pre-hydrolysis reaction condition on xylo-oligosaccharide extraction in eucalyptus globulus. In this work, we studied the possibility to recover high-value compounds from the pretreatment, with special focus on xylo-oligosaccharides. The effect of pre-hydrolysis condition and the difference of flow-through versus batch reactor in the final pulp was also analyzed. Throughout this work, the influence of temperature and retention time is shown to have a great effect on the xylo-oligosaccharides degree of polymerization. When comparing batch versus flow-through reactor, the difference of pulp yield was 2%. However, it's well known that precipitation compounds may occur in the batch system, which can overvalue the yield. Pre-hydrolysis kraft is the alternative of the kraft cooking. In this process, the wood is pre-treated, aiming to remove a high quantity of hemicelluloses prior to the kraft. The final pulp obtained have lower viscosity, higher reactivity, and higher cellulose content. The two-step cooking also allows to recover compounds released during the pretreatment, mainly hemicellulose. From the different compounds, we'll focus on the recovery of xylo-oligosaccharides, being the only compound with pharmaceutical interest as probiotics. I'm talking a lot of xylo-oligosaccharides, so what are they? Xylo-oligosaccharides are sugar molecules made up of several xylose units between 1 to 10. Lower degrees of polymerization have a special interest by having a higher probiotic potential based on the selective metabolism of bifidobacteria for these compounds. We'll focus on the extraction of xylobiose and xylotriose. The system used for the flow-through reactor allowed the control of flow or retention time and temperature. The samples were collected after cooled and analyzed by high-pressure liquid chromatography. The important part of this method is the ability to recover samples throughout hydrolysis, which gave more information about the different compounds released and the kinetics of extraction. The kraft process for all the different pretreatment conditions were the same. Table 1 resumes the total amount of xylo-oligosaccharides throughout the pretreatment. The first and second assay differ in the flow rate, which affect the retention time of the two compounds inside the reaction. By comparing these two, it's feasible that a higher retention time will result in a higher quantity of lower degrees of polymerization. However, like I said previously, xylobiose and xylotriose between the different xylo-oligosaccharides have special interest, and in this case, higher flow rate allows the recovery of a higher quantity of these compounds. By increasing the retention time, xylobiose will form xylose, decreasing the value of the recovered samples. Between the second and third assay, the temperature of the treatment is increased. In this case, a higher temperature will induce more degradation products like furfural, and the lower xylo-oligosaccharides recovery yield is achieved, with poor results not being the purpose of this work. The batch system, the retention time is the total time of the treatment. As identified before, a higher retention time will affect the degradation of xylose. In this case, the furfural reached 82% of the total xylo-oligosaccharides and furfural recovered. To add more information to this study, the composition of the pulp was also analyzed. The batch system had the highest hemicellulose and lignin content, which can be explained by the precipitation of compounds during the pretreatment time. Between the samples from flow-through, there was less differences. Other interesting point was a difference in pulp viscosity between flow-through and batch reactor, which need further investigation, but highlights the use of flow-through pretreatment to enhance dissolving characteristics in the pulp. Some of the results show that the highest quantity of cellulose-based recovered was achieved for the bread method with lower temperature and retention time. In this assay, 40% of the cellulose-based extracted were cellulose and cellulose. We also saw the effect of the batch system, which led to much lower cellulose-based recovered. The final pulp with higher cellulose content and better dissolving characteristics was achieved by the flow-through system. These results guide us for future works where it could be interesting to investigate the bleaching and dissolving response of the different pulps obtained. Together with this analysis, it's also interesting to analyze the structural changes of the pulp. And that finishes it. Thank you very much for your attention and feel free to ask any kind of questions.
Welcome back. So I'll ask for all the speakers appear on the screen, okay? And we have a few questions now, but first of all, I have to thank all of you for the presentations, and I'm going to follow my list of questions, and because Francisca cannot be present at this moment, and I'm an author of the first work, I leave the question for the end to myself to answer. Okay, so the first question will go to Álvaro, okay, Álvaro Vaz, and the question is, in the breach jar separation, continuous water supply and recirculation methods were referred. What are the advantages or problems related with the recirculation method versus the continuous water supply?
The point is that we lost the fibers in the continuous process, and there was a problem of high consumption of water and also the loss of the fibers. So we devised the system that with the recirculation to recover the fibers. That was essentially the problematics that we faced at the time.
Okay, I understand. I think you answer well. Okay, so I'll ask Flavia Moraes now to ask her a question. And what is the mechanism by which the incorporated microfiber and the nanofibers in the tissue paper formulation affects the final material, making it a premium material?
Well, I incorporated this additive as an additive. We use cellulose, micro nanofibrillated cellulose in the suspension. So we mix her with the fibers, and then we produce the tissue materials and evaluate the properties of the tissues, like softness, strength, and absorption. And in our results, we found that the micro nanofibrillated cellulose up to 8% of incorporation can present better results than the use of tooth pulps. So we can use it as an additive and improve the properties.
Okay, but the most concerned property is the softness, or
no, the strength.
The strength, okay, mechanical properties, okay.
Yes, mechanical properties increased, but we can assess the balance and the trade-off between the three properties up to 8% of the incorporation.
Okay, thank you. Now I will ask for Mohit Sharma a question. Mohit, what are the environmental environmental implications of adding cationic stretch to the paper, namely for the paper recycling?
Thank you for the question. Actually, this which I present, the starch betainate, the cationic starch, which is completely based on bio-based polymer, like this betaine hydrochloride, which we use for the cationic for obtaining the cationic starch, which is completely bio-based. And earlier in the commercial available cationic starch, they are based on different reagents such as FibEnTech and all, and they
Yeah.
are more problematic. But this starch betainate which I presented, it's recyclable, completely recyclable, and it's really improved properties also, like they are comparable to the commercial available cationic starch.
Okay, thank you very much.
Thank you.
Okay, now we have a question for Manorma Charma. Manorma, thank you for the presentation. How are you planning to develop a greener alternative for the described experimental design?
Thank you for question. Actually, I removed this isolation of lignin. We saw the organic acids, which are greener alternative what we are presently using. It's sulfuric acid mainly. They use for separation of lignin. So that's why we are trying to use greener alternative. That's the process. And for hemicellulose separation, we are trying acetone, but more than that, we are also working on ethanol use. And because we are separating both lignin hemicellulose with greener anti-solvents. So I think it's we are using complete we are extracting complete biopolymers from the black liquor and using the greener anti-solvents which don't have much impact. And later on, we are trying to recover these anti-solvents also. So I think process is not going to have any kind of residues to discard. And I will say more specifically harmful residues to discard. So I think this process is greener.
Okay,
Yeah,
great, thanks. Okay, now I'll call André Cunha. André, the question is, why such a difference in viscosity from the batch and flow-through process?
That result must be further studied, but for example, in the batch system, we used autohydrolysis, while in the flow-through reactor, we needed to get the pH value close to the final part of the batch system. So use the acetic acid to lower the pH, and the relationship between acetic acid and the autohydrolysis process may influence the viscosity.
Okay, thank you. And now I should ask Francisca, but Francisca is not here. I'm going to ask myself a question. The question is the fibers concerning the work of Francisca presented, concerning the holography of microfiber 3D imaging. The fibers were analyzed in two dimensions, in a lamella or in 3 dimensions. Okay, the answer is the fibers were analyzed in 2 dimensions in a lamella. You are right. And those has no depth and is purely 2D. The answer is yes, right. How does the analysis of the fibers compare with the USAF? Okay, only for the focusing purposes at the moment, because we intend to use this system to create a tomographic reconstruction of the fiber. So the first step is using this setup to obtain an exact focus of the element. And now using a tomographic setup, we will reconstruct the the fiber in 3 dimensions, the fiber or the crystal or what do you want to observe. Okay, I think we are just in time to finish. I call all the authors here. I have to thank you all again. So, and the afternoon session for the first technical session will start at 12, at 14, at 14:30 minutes, okay? So I'll ask everybody to be online at least 15 minutes before the start, and we will see you later. Have a nice end of the morning, and thank you again, and have a good lunch. Thank you.
Thank you.
Thank you. See you later.
Thank you.
See you later.
See you later.
See you.